Who here knows about Cloudflare? Oh, okay. So I'll not explain what we generally do. I'll just talk a little bit about myself first. So I do Linux at Cloudflare. I manage the operating system we run in production. I'm passionate about system security and performance, and I enjoy low-level programming. There's kernels, drivers, bootloaders, and other stuff written in unsafe programming languages. I'm also a die-hard Linux fan, and you can see that I'm presenting from a Mac now. So and there are reasons for that. So Linux is great, but it cannot do two things. One is connect to external projectors and power management. So, so yeah. Okay. Today we're going to talk about TPMs. Who knows what a TPM is? Trusted Platform Module. Who here has a laptop? Who here thinks that their laptop doesn't have a TPM? Okay, so you'll see. So yeah, a TPM is a small, often discrete, but in modern hardware, it can be integrated security chip. It is present on most modern laptops, and not even modern, I think it has been around for many, many years, and servers alike. Yeah, it's a passive and non-intrusive device. It's not like some other security systems that are very, try to spy on you. It's passive. It only responds to commands and performs stuff if you ask it. If you don't ask it to do it, it will not do anything. So it doesn't tap into memory or anything. But even though it's a very cheap, low-powered, slow device, it allows you to build a great foundation for platform integrity, authentication, and remote attestation. And luckily for us today, it's a crypto chip, so it can handle cryptographic keys, which is good. If you ever been to previously to any TPM talks, most talks and blog posts out there and everything is all about TPMs and remote attestation, right? Anyone here doesn't know what a remote attestation is? So yeah, remote attestation and platform integrity. So the primary usefulness of the TPM that you can remotely attest your hardware and ask it are you running the operating system I expect you to run? Are you running the patches you expect you to run? Did you have the proper boot cycle? So you can remotely have guarantees of assurance of a state of a platform at a particular point of time. And it's a really nice feature, for example, even for server deployment, in Cloudflare, we have many, many servers around the world, and we have data center locations where there was never a single Cloudflare employee even visiting it. So but still, as an operations team, we can say okay, I know what this server is running right now, which operating system, which software, just because we have a TPM and it can provide this information. But TPMs are great, so operating system use it, vendors use it, Windows uses it, everything, but it's available on every machine. I had a question is, why there is not much open source or commercial software actually utilizing TPM for storing your cryptographic keys, right? So we all use YubiKeys, we all use fancy mobile authentication. You have a super secure chip in your hardware right here, right now, and there is actually almost zero software which can utilize it, right? So the question about this presentation is not about remote attestation, it's about, as a developer, I'm a software developer, imagine I just want to develop a tool which stores cryptographic keys on the TPM. Can I store my keys in the TPM? Yeah, and this is basically my mental model as a developer, right? So I write code, there is a TPM, I want to use it, right? Unfortunately, apparently it's not that simple, right? My code runs on a computer which runs, modern computers runs operating systems. So you most likely use an operating system, and if you run an operating system, you cannot talk to a hardware directly, right? You need to use operating system abstractions because the operating system mediates applications and access to hardware. So if I run, for example, on Linux, and we'll be talking about Linux today, like to access the TPM, my application needs to talk to /dev TPM0, like a Linux device file representing the TPM, right? So, well, okay. But it's not over yet. So like, to talk to the TPM, you need a thing called a resource manager. And the problem is TPMs are nice because they're super cheap. So for vendors, it's almost have zero cost putting them. And if it breaks, it's like a $5 replacement. But on the other side, they're not very powerful. And they don't support, multi-tenant access, like simultaneous access. And like most likely, if you run on an operating system, you have a multitasking, right? So like there may be many applications trying to access the TPM. So what Resource Manager does is kind of serializes its access so the TPM doesn't get confused, right? So I need this Resource Manager. Well, and not only that, so I also need a TPM library, right? So like to talk through the Resource Manager to TPM, I need some kind of high-level abstractions to talk to me. So like my initial mental model was application TPM, but now I need all these things and know about all these things, right? So now let's zoom into the Resource Manager specifically. So the other problem with the Resource Manager, the first implementation of the Resource Manager was a daemon on Linux, right? It was like a user space service which mediated this access. And it is very confusing for developers. So like from your perspective, you kind of try to access a device, but what if like that daemon is written in C and like it may crash or didn't start or the system may be misconfigured. So like from my perspective, I'm trying to access a device, I know it exists, but because some service is not running, like my application doesn't work. So like this sounds not very convenient. So I think like Linux kernel developers like recognize this, and in modern Linux kernels, they basically re-implemented the Resource Manager directly into the operating system. So the kernel always runs, so the Resource Manager is always running. So basically now if you want to use in kernel Resource Manager to access the TPM, you need not to talk to /dev TPM. You need to talk to /dev TPM RM, which stands for Resource Manager, a different device file. So if you're writing software talking to a TPM, never talk to TPM device directly. Talk to the Resource Manager. Okay, let's move to the TPM library, what we can use these days. And the situation here is not better. So we have like two major competing implementations. One is called Intel TSS. TSS stands for Trusted something. TSS stack is like Trusted Software Stack, yeah. And we have an implementation from IBM, like two major companies proponing TPM usage. The problem with these, they cannot both try to follow standards, but the standards doesn't define APIs, so like they have completely incompatible APIs. So for example, you have to choose either you use one or the other, or you write a wrapper that you can use both, but like you have to do more work here because, for example, if you want to package your application for major Linux distributions, you cannot be sure if the distribution provides either this or that or both. So like you have to think about that. So there's a lot of stuff going on. And these are like C implementations. So if you, for example, write your code in Go, like Go people, they don't even like external dependencies at all. So they say like, oh, Google implemented a pure Go implementation of the TPM library called Go TPM. And to be honest, I never checked the Rust space these days, but I'm sure maybe there is a Rust implementation as well. So like, yeah, so like you also need to understand what kind of TPM library is available. Can you rely on that, or should you bundle it, and other stuff. If you go to the GitHub page of the TPM to software stack to understand what that stack is all about, you'll see this slide, right? And they will say like, oh, you have these various layers where you can hook into. You have like the lower layers, which is my closer APIs, the high levels, which give you like more abstracted APIs, but you can do less things, or you have a middle layer, which you can basically reconfigure. Like, like it all becomes really, really confusing. Like you just want to talk to a TPM and store the key, right? But imagine you like understood all of that. You researched it. You're now a TPM expert. You're finally ready to write code. So you write some code, and the problem with this, like your code, you have like, if your application will try to access the resource manager on the operating system, you'll get permission denied. Why? I mean, and this is like basically a standard bare bones Debian installations, for example. Why? Because, well, on the standard Debian installation by default, access to the TPM device is only allowed for root, and the same for the resource manager. So like, you know, like you write your code and you have to package it that it runs as root privileges, and then like if you want to officially distribute it from Debian folks will ask you like, why does your application need to run as root? Like it's a privilege escalation, right? More confusingly, if you, on Debian at least, like if you do install the Intel TSS TPM2 tools which use Intel TSS stack, you will notice that the permissions will change on the TPM0 device. Now it's owned by a special TSS user, and yeah, and TPM resource manager will owned by TSS user. Oh, here I have, and TSS group. So you can technically put your user from which your application runs from into TSS group, and it can access TPM. But again, you have all these packaging problems, so you have to package for every distribution, like understand how it works, you know, like you have to convince the developer if you want to distribute your package officially that you need to be in this group, and like you have to understand how your users will run the software. Will their user be in the TSS group? Like, and for example, if your application is written in Go and you don't use the Intel TSS stack, do you need to have TPM tools still as a dependency so you get this configuration? So yeah, it's very, very complicated. And that's why like most software just don't do it, right? Because they can't figure all these out really well. There is another way, like who've been here in 2023? Oh, a couple of people. I don't know if you attended my talk about the Linux kernel key store. So, and if not, it's okay because I'm going to repeat some of this here. Linux has a cool feature called Linux Kernel Key Retention Service, aka I call it key rings or key store for short. Who knows that Linux has a key store? Okay. Yeah, so for those who doesn't know, like key store is kind of like similar like keychain on Mac, or I don't know what's the Windows equivalent where you store certificates and stuff. Crypto providers it was, or something like that. Yeah, so Linux has this service, and what it basically is like, let's imagine you have many applications which run on Linux. Obviously, you have the Linux kernel because you run on Linux. So the Linux kernel provides to applications basically 3 specific system calls to manage keys. And applications can use these system calls, for example, to store keys as kernel objects inside the kernel. And originally, it was designed to provide cryptographic information to the kernel for in-kernel subsystems. So for example, if you have full disk encryption enabled, which you should, you need to provide the password to unlock the disk, right? So the kernel needs to know your password, so these system calls are the interface, the applications, your like password unlocking program will provide it to the kernel, and kernel will use that password to unlock your disk, for example. But eventually it was extended that applications also can use these keys that you provide to the kernel. So some applications can provide keys to the kernel, the other applications can use those keys. So like the keys are kind of stored inside the kernel itself, but applications are using it, so it's kind of like a software HSM model, where keys are kept separately from the application address memory space, which is really good for security. Who here remembers Heartbleed? Oh, yeah. So like if you store your TLS key in kernel key store instead of like in OpenSSL, you would not be affected by Heartbleed. And internally, keys and inside the kernel represented as a collection of key rings and keys. So key rings may contain other keys, and also key rings may contain keys. So it's kind of similar to a file system hierarchy, where key rings are directories, like collections of keys, and the keys themselves are files, the objects that have the cryptographic data or secret or whatever, right? Probably the difference is like a key can be in two key rings simultaneously. So, and the key presence in the key ring defines the lifetime of the key. So, for example, if this key, I will remove it from these both key rings. So, like a key cannot exist independently without any key rings. The operating system will destroy it securely automatically. So it will release the memory backed by this key and zero it out. So it's very great in terms of even like secure key deletion. So here is, for example, a basic example of a Linux kernel key store. And if you heard my presentations before, I like to say that all these commands are copied from a real terminal from my Debian machine. So consider this as a demo, but unlike the demos we see yesterday with Michael Karask, it doesn't fail because yeah, but you can like walk through and copy paste all of that and you should get the same result mostly. So yeah, we have like two users on my system, so Alice and Bob, and we can see that they don't share any credentials. So they have separate user IDs, they're not part of the same group, nothing. They're like just two separate users, right? And let's imagine Alice wants to share a secret with Bob somehow. So Alice can use a kernel key store. So what Alice does is Alice adds, with this command, Alice adds a key, a secret basically, with the contents of Hunter2 to Alice key store. What Bob can now do, Bob can now create a new key ring, which is basically an empty collection of keys, and let's call it from others, so to receive Alice keys. Now what Bob can do is like, because it's a proper kernel object now, it has associated permissions, similar to like file permissions, but there are like more permissions on the kernel key object. So what this means is basically Bob allows anyone on the system to write to the keyring, and writing to the keyring means putting keys there, right? So it will make it like world writable. So now Alice has access to that keyring. So Alice moves her key to, and every object, like both keys and keyrings, are represented by this unique number called a serial number. So like now Alice can use that serial number and move her key to the Bob's keyring. And now Bob has the key and Bob can actually read out the secret back. So like Bob now has a secret, and you can also see that Bob now possesses this key, what's called like having a key in your keyring means key possession. And Alice actually, because we moved the key, doesn't have the key anymore. Alice cannot read that secret at all. And Linux kernel key store provides several key types. So the example we just saw is the simplest key type called user key. And the user key is basically a buffer with secret or bytes. So one process can put that key inside the kernel, and either the same process or another process which has appropriate permissions can read that key back. There is a variation of user key called a logon key. Logon key is kind of the same, but once you put it inside the kernel, no matter which permissions do you have, you can never read it back. And why it's useful? It's exactly useful for providing cryptographic material to in kernel subsystem which need access to it, like disk encryption. So if you have a recently modern Linux distribution, you will see that your disk unlocking password is actually provided as a logon key. You provided it in the kernel once on boot, but you technically never need to read it back. So it's inserted in the kernel as a logon key. Yeah, there is also like asymmetric key support, which I think is cool. So imagine you just don't have like a string of bytes of secret, you have an RSA key. You can put it inside the kernel, and another process, instead of reading it back, if it has appropriate permissions, it can perform cryptographic operations with that key. So it doesn't need to read the key, but it can say, hey, kernel, please sign me this data with the key you have, which is referenced by the serial number. And this is where it became cool, like the kernel becomes your like soft HSM or a soft token, right, to handle your keys. So sounds good. Like we have this software HSME subsystem. We have TPMs, which is supposed to store cryptographic keys. Would it be better to somehow combine them together, right? Like in a very useful primitive. And Linux actually kind of does it, but like in a very specific case. So there is a key type called a trusted key, and the trusted key means, like on the previous examples, the problem is that with user keys, that even though you can insert it to the kernel, the process itself that inserts it that still has access to plain text cryptographic material, right? So there is still a window of time that sensitive material is available to the process. So if you still have a heartbleed type of vulnerability, which is triggered at that exact moment, that memory can be dumped, and then your key will be leaked, right? Would it be better to somehow design a system where the plain text secrets or key are never accessible to user space, only inside the kernel, which is literally better protected? So this is where wrapped keys come in. So a wrapped key is basically an encrypted blob with a secret encrypted to a particular TPM. So when some process inserts the wrapped key, the kernel internally talks to the TPM to decrypt it. So in the kernel space, the key exists in plain text, but if you try to read it back, it's always automatically wrapped to this TPM again, and in user space, it's always in an encrypted blob. But it's good, but up until recently, it wasn't very useful. So the only useful feature for that was actually, again, providing you the ability to provide your disk encryption password in encrypted form to the kernel, like nothing more, because like in the process, you could not use that wrapped key at all because it's always encrypted, right? And this is where there is another subsystem called Linux Crypto API in Linux, which is different from Linux Kernel Key Store and is different from TPMs. So as Linux Crypto API, you can use the Linux kernel as a crypto library. So for example, if you run Linux on a small IoT device and you don't even have space for installing OpenSSL to do crypto in your software, you can actually ask the kernel to do it. And the way how it's done, you create a special socket type. It's not a network socket, but it's a socket basically from your process to the kernel. And this crypto socket will instantiate like an instance of an encryption algorithm in the kernel. So, for example, AES, right? Now, you as a process, you are responsible for providing cryptographic material to initialize this instance. So what you have your cryptographic key, which is an AES key, you send it through the socket, and the kernel instantiates this this encryption algorithm, and now you can send some data to that socket, and the kernel will encrypt this data with this key and send the data back. The problem with this, and this is where I say the Linux Crypto API is independent from the key store API, this is not a kernel key store key. So these are totally different subsystems. This is just a byte buffer in your application, which was silly. So like, we saw that as an opportunity. So what we did is we proposed a patch to the Linux kernel to actually combine these two subsystems and allow you to, instead of providing a byte buffer, to encrypt something with the kernel to actually reference a key store key. And so what you can do now, and this makes actually wrapped keys much more usable because, for example, you provided a wrapped key to the kernel, it's in plain text in the kernel, but now you want to use it somehow. So you have a process 3, for example, which will create this crypto socket and instantiate an encryption algorithm, but instead of providing the key directly, this process will say like, hey, I want this algorithm to reference this key, and then the kernel will do it for you. And now you can kind of like, insert a wrapped key into the kernel, you don't know what the contents of that key, but you can still use it and encrypt data with it. Yeah, so now the applications can decrypt, and it even brings you even more closer to a proper software HSM. And if you want to use this functionality, it's been merged from Linux 6.2. So if you run an older kernel, it's not available, but if 6.2 and onwards, it's available. The problem with this approach, it only supports symmetric keys for now. So you can only encrypt and decrypt data, but you cannot sign or verify. For that, you have to use the asymmetric key type, which is different. And we also wanted to kind of fix that and connect it all to the TPMs, but actually the Linux kernel developers are already on it. So there is a patch set which has been developed by the TPM maintainers for a couple of years. So hopefully they'll merge it soon. The problem with this patch set, though, so it kind of like will allow you to do this. So like this is a simple signing key, right? So you have the signing key, you can use it. So now we want to bind it to TPM, so we can never see the plain text asymmetric material. So they will do something like that. So you have an RSA wrapped key, and you insert it to the kernel, and the kernel, instead having the plain text, and the kernel will handle it to the TPM. So the key will actually reside on the TPM, and even the kernel will not have the plain text cryptographic material, and then you can use it. But there is kind of like inherent problem, several problems with this approach. The problem number one is like if you do everything through the TPM, remember at the beginning of the talk I said like TPMs are slow, right? So like you can not put actually many keys like this, so you cannot, if you manage a web server, you cannot put your TLS key there to protect it because basically your web server will be slow. Your TLS handshake will be too slow. There is another problem with these wrapped keys, and like the fundamental problem is the way how they created. And the way how they created, so you have a random number generator, right? How do you create keys? You generate them randomly, right? So you generate some keys, then you basically take your TPM and wrap this key into an encrypted blob. Which brings us to the next problem. So this approach solves the fact that your key is now protected, but it has a really poor key management part. So imagine you can do all of that, right? But what if, even though your wrapped key is wrapped, what if you lose it, right? What if you wrap your disk encryption password like this, and you lose that blob? You don't know what your disk encryption password is because it's encrypted, so you cannot recover it, and you use that blob, so you cannot unlock your disk. So yeah, so where to store these wrapped keys? Like obvious case, you will store them on disk, but like at least like what we have at scale problem, and you might even have it on your laptop. What about like diskless systems, right? So where do you store your wrapped blobs? What about if your disk breaks and you don't have any backup copies? So now you have to think about proper key management and doing backup copies. What if you just accidentally wipe your disk? It happened like in our production environments. For example, a configuration management was misconfigured and it wiped a server. Everything is lost. And like you don't even have to wipe all the data. You only have to wipe this small blob, and then boom, you can't decrypt your data anymore. And the fundamental problem with this architecture is also you want to have a unique key per application, right? So if you write many applications, every application should use dedicated key, so you have one blob. What if you have more services, you have more blobs, and you have this like all extra state, which is really, really critical for you that you have to keep an eye on. Like you have to store it somewhere, you have to back it up, you have to do all these other things. So I've been thinking, like, is there a better way? And what if we like flip how we actually generate keys? What if we turn wrapped keys into derived keys? So like the way how we create keys would be different. And we can do that with a TPM. So with a TPM, every TPM has a so-called seed. There are like more than one, but like for the purposes of this presentation, seed is like a very secure, large cryptographic material which is unique to your TPM. And by TPM design, by all the standards, you can never, 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 ever get it from the TPM. So it's like an internal TPM, an internal like secure string unique to the TPM. What the TPM does provide is how to access that seed is a key derivation function. So even though you can't access the seed directly, you can kind of derive keys from that. And all this is mandated by the TPM standard. So like every TPM should have a seed and a KDF. Like if it's not, it's not compliant. So you can rely on the fact that every TPM has that, right? So what if we, instead of generating keys, what if we use this approach, and to make the key unique per application, we will provide I call it a mix-in, like an application metadata, which is unique to an application. But it doesn't have to be secret. It can be like anything, like in the examples that I will show later, we can use like the pass on the file system, right? Or something else, like any application metadata, which uniquely defines an application. So we can generate reliably a key which is unique to application and based on the TPM. And the nice thing about this approach, so that's how it scales, right? So imagine we have many, many applications and services for which we want to have a TPM-based key, so we generate one. If we have more, we can generate as many as we want. As long as this mix-in will be unique, we can generate many more keys. But the nice thing about this approach, this is totally disposable state, right? Because the process of key generation is totally reproducible from the TPM. So you don't have to store all of that. You can basically do this on every machine, on every boot. For example, imagine you have a diskless small IoT device where you want to SSH into, right? So anyone has a Raspberry Pi or something like a project at home, and like if you don't have like persistent memory, if you SSH into that, you will always have a random key, and your SSH will complain, oh, that key is different from what I've seen last time. Yeah, like would you like to accept it? So like it's not a great security. What if using this approach, you can have a static SSH key even on a diskless system, because with every boot, the software will be able to rederive that key back from the TPM seed, which is static. So how to implement all of that? So, and to do that, I wanted to explain the difference of two system calls in Linux. It's called add key and request key. They're both part of the Linux kernel key retention service, but they have just semantic differences. So with add key system call, and we've been using so far add key in our examples, the process itself is responsible to providing cryptographic material to the kernel. So what the process is doing is like, hey, I have some key material. With user key, it will be a plain text cryptographic material. With wrapped key, it will be encrypted block. But the process needs to get it from somewhere, right? And it uses that key. And the semantic is, hey, kernel, here's my key. Put it inside you, right? So and the kernel does it. Request key is different. With request key, it is assumed that the process itself doesn't have any access to any cryptographic material. Instead, it says to the kernel, hey, kernel, give me the key, give me my key, right? So like, give me the key from me, which I need to know. And the kernel is actually responsible to somehow find a key for that process. And of course, everyone's setup is different, and the kernel by itself doesn't know where to get your key from. So what it does, it creates a placeholder. But what you can do to configure your system, it will create a user space, a special user space process in the Linux kernel terminology is called a callout process, which is located, any binary which is located at sbin request key, and say, hey, help me to find this key. And you as an admin, you can reconfigure that process or even write custom modules to it to handle specific key types. So for example, if the key ID is, you can parse that key ID and say like, oh, the process requested the key from, I don't know, my Amazon KMS or my local Vault instance or something like that. So you can actually satisfy that request. And I was thinking like, what if I write a module where the request would be satisfied with a TPM? So like I wrote a module which basically redirects the request back to the TPM. And what happens is like if the process requests a key, the plugin properly works and it kind of like generates a key derived with that architecture that I presented, returns it back and down the kernel that has the key, and the kernel basically notifies that the process that your key is ready, you can use it. So in this case, basically the process doesn't have to even know what key it needs. It kind of says like, hey, give me my key and here's your key. Yeah, and this plugin, this is a short link. It's located on my GitHub. I can share the link. I will reshare the link later. I'm sorry, this is like a proof of concept. So it's not, it's written in Python and not a real programming language. So yeah, but you can go and download and try it out. And what it does is basically it generates key, not generates, but derives key from the TPM seed reliably based on application metadata, on the application which requested. And now you can do very, very interesting things. So you don't have to fully understand what this does. It's basically a way to configure, if you download my plugin, how to reconfigure your system to actually use it. So what it basically says is, if an application requests a key which starts with an ID TPM2 derived, and whatever the name application gives here, invoke my plugin, which will talk to the TPM to generate that key. And now we can test it, right? So imagine I will not write my own code, but I will use the Linux-provided system called wrappers as tools. So imagine my application wants to request a key, and so like it issues, give me my key. It has to be a user key, and the key ID is TPM2 derived test. And it can also provide some parameters. And I've implemented at the beginning that it actually parses two parameters. The first one is 32, is basically the number of bytes the key should have. So I'm requesting a 32-byte key. And the second parameter actually tells my plugin which application-specific metadata to use to make this key unique to my application. And in this case, I tell it, hey, use my path, right? Yeah, and like you see, the request will be satisfied, so I get my key back, and I can actually print it out. So if I print this key, I get some generated key here, right? And it will be unique to my application. And now to show you that it's unique and fully reproducible, I can delete it. I can delete it. So the kernel will wipe the memory securely, as it should. And I can request it again. And now you can see from the kernel perspective, I'm getting a different key because I'm getting a different ID here. So the key is regenerated. But if I print it back, it has the same contents. So this key is unique to my application, and I don't need to worry about storing it anywhere. I can always recreate it when I need it. Cool? Yeah, so now let's delete. Now let's actually check that it kind of like, it is unique to my application. So I delete the key again, and what I do now, because I requested a path as an application metadata, I copy my application from one place, it was in user bin, to my home directory. So it's now in a different place in the file system. I will rerun it with the same arguments, but then I have a different key, because now my application is located in a different place on the file system, so I will get a different key. This is how you can, for example, do the static SSH key for the SSH daemon. Yeah? Whatever is located at user bin SSHD or sbin SSHD will get an SSH key for your system, right? But no other executable on your system will be able to get the same key because it's unique to that particular application. I also wanted to show you, so we're also taking a user ID into the account. So like if I basically rerun the same thing but with a different user, I also get a different key. So for example, an application may have permission bit 755 executable by anyone, right? And if different users can execute the same binary, they should generally probably get different keys for that, because otherwise you can execute your SSH daemon as your user, not as root, and then you can kind of leak its unique key, right? Which is not great. There is another option I've implemented in my POC plugin. So I request a different key now instead of, well, the same ID, but the metadata instead of pass, I tell it keyword checksum. And a checksum means a checksum of the application executable itself. So now I'm binding my key to the platform via the TPM, and I'm also binding my key to the executable code itself, which was requested it. And this is pretty cool as well. So like, yeah, I can print it. It has some numbers. I can delete it again. Now, because I'm using a different metadata, I can move this application from one path to another. I can move it from keyctl1 to keyctl2. I will re-request it, and I still get the same key, right? So because wherever I move this, I can move it anywhere in my system, but the key is bound to the executable itself. And to prove that, now I'll patch my executable. So I know the keyctl utility has an error string called bad message. So I'll just change 1 byte here. I'll change bad massage. It will still work, right? But 1 byte. If I rerun it, I get a totally different key because the executable changed now, so the key is different. Okay. Similarly, you can also do asymmetric keys with my plugin. So you can request an asymmetric key type, and you get some key, and now you can generate some test data with OpenSSL, and you can ask the Linux kernel key store to sign it. So like you get some signature. You can delete the key. Because you cannot actually read asymmetric keys back, to prove it's the same key, I will delete it, recreate again, and generate the signature again, and you see the signatures match because the key was reliably recreated, and yeah, you can, and it's specific to your application. So yeah, I find this architecture really, really well. There is one small thing I still don't like about it, right? So like, there's still this place where the key exists in plain text in user space, right? It's much better than before because it only exists in this special like privileged process. It's not existing like in your regular applications. It's only one place. So, and in modern Linux distribution, you have address memory space isolation. So you will still probably not be affected by Heartbleed. But like it would be even better if we just can cut this like middle piece, right, and just like do this. But for this, we need kernel development. So, and for historical reasons, we need to replace the request key system call for add keys, and we would want to have something like that. And the reason is basically because RAP keys are using this, where RAP keys should be using request key properly. So I actually proposed a patch set to the Linux kernel last year, actually implementing all this, but inside the kernel, and describing all my use cases, everything that I told today. The first feedback was like, I don't honestly believe that this library solution for any possible problem exists on this planet. Partly, this is why I'm doing this presentation. Do you think it is useful? Yeah. Yeah, so I can like feed that data back, and like, but after some back and forth, I think like we reached an agreement that we should continue researching this further. Like the kernel folks propose some good improvements, for example, so you can make For example, what they said, like the concern was if you implement it in the kernel, let's say you use the kernel to generate a key in the TPM, but then you have root privileges on the system and you talk to the TPM directly and kind of steal that key because you can regenerate it, right, and steal it. So they say, like, how can we address that? And my idea was through patching the TPM driver, we can actually probably reserve a whole namespace of keys specifically for the kernel. So for example, if the key starts TPM2 derived kernel blah, 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 only the kernel can generate this key from the TPM. And if a user process tries to generate the same key through the user space interface, the driver will say, like, permission denied, for example. This is where you can even be even closer to like a proper HSM, and you can have like hardware security, and you can have the static keys, and you can have disk-link system. You can have so many nice things. All right, that was, I hope, not too much information. Conclusions. But yeah, the whole point of this presentation was interfacing directly with TPMs is very hard, but kernel key store is this really nice abstraction which is available to every application. You don't need special permissions to talk to it. Yeah. So interfacing with TPMs is hard. So that's why most applications avoid them altogether. Yeah, Linux kernel key retention service can be a good this abstraction layer to abstract the TPM interaction complexity for application. But as you saw, like some additional development might be required. You have to either you plug in or wait for the kernel stuff to be merged. But TPM derived keys is probably a very good alternative to TPM wrapped keys. And it provides kind of similar hardware-based security guarantees as wrapped keys, but with potentially really, really much easier key management. And currently, you can even use it now. It can be implemented via request key plugin for current kernels. Like you can go and just download and improve my plugin or rewrite it in a proper programming language. Or you can wait for in-kernel version to avoid exposing the plain text material to user space. Yeah, and like exposing TPMs through Linux kernel key store can provide applications to these straightforward path to adopting hardware security, because from an application perspective now it's just talking to the operating system through system calls, similar to reading a file or doing network I/O, right? And also it's probably true for other security chips. I know like mobile phones have security chips these days. Some companies do their own chips like Titans or like whatever like Amazon does. So if you're involved in development of any security chip, do consider exposing its key store functionality through the Linux kernel key store API, because if you do that, like any application on the system can now easily use your hardware without like needing any extra software dependencies. Well, that's basically it. Here are some useful links. So the first two are the documentation for Linux kernel key store and the trusted keys in particular. The third link is an ongoing effort for TPM maintainers to implement an asymmetric TPM-based key. The fourth link is an extended link for my Python request key plugin, which you can go and download and play with it and copy-paste all the code from my presentation. But you have to be prepared. Your output will be different because you have a different TPM and different seed. And if it's not, please tell me, because because there's probably a vulnerability somewhere, right? Yeah, and the fifth is like follow this work if you want to follow along and see like if the in-kernel versions will like make it into the kernel and you can start using it. Thank you very much, and I think I have some time for questions. Any questions? Yes?
So this plugin that are those derived keys still bound to the user?
Yeah. If you go into the code, you will see like when the plugin receives a request from the kernel, it checks like, okay, which application requested it and which user ID. Yeah, so like it will use all that metadata to fit into the KDF hash function to generate this unique key. And you can probably tweak it with other use cases. Like this is a nice thing actually about the plugin itself, so you can actually retweak it to the metadata you think it is important, and you can like implement new metadata types. You can make some metadata optional, some metadata not. So like depending on and what you want to do. Because like the reason I've implemented even two parts, because I think like the checksum metadata is cooler because it's like securely binds your key to your application, but then the first question comes out, how do you do software updates, right? For if your SSH daemon updates, like your key is invalid, which is not great. That's why like the pass is also a useful option. But maybe there are others.
A follow-up question on the path, because I mean, for example, file system namespaces,
Mm-hmm.
you bypass that?
So, good question. I forgot to check this, and I probably should. No, I mean, generally you can't bypass because I think I have to check, but the kernel key store itself is not properly namespaced. I think it's like only namespaced by user namespaces. So basically when the request comes into the kernel, when it goes out, it kind of strips all the container information, which is kind of like a bug and a feature at the same time. Bug because like you cannot like containerize this, but a feature, for example, it allows you to use this in a multi-tenant system, right? So for example, imagine you have a Docker cluster, a Docker node, right? So and containers request their keys, so you want host to be in the control which keys you provide to containers versus each container doing their own thing, right? Yeah, but I mean, technically, because the plugin itself executes in the host namespace and it executes with root, you can literally make the checks as strict as you want. You can go into proc file system and you see if it's a namespace, if the user ID is namespaced, and like all sorts of things. Yes?
Have you seen any analogous approaches to key generation with TPMs in other like operating systems, platforms, maybe? I'm just curious if there's any other perspectives out there, like good ways to sort of.
No, to be honest. And this is where I even like from seasoned kernel developers, I met, I don't know if you know, James Bottomley, who is considered to be the TPM guy in the world. And like he's like, why do you have this problem? Like, why don't you store it on disk? Like disks like fail and they're not always there, right? So like people just don't consider these cases. I never saw that similar perspective, and that's why I went to the rabbit hole of developing it. But to be honest, in Cloudflare we use a previous version of derived keys. I had a talk about this myself, like 7 or 8 years ago, which doesn't use TPM, but it uses a similar approach, and it worked for us as a key management like really, really well because of this derived unique key approach. You can really scale your keys to millions of servers, millions of applications, and you don't have to worry too much about backing those up because you eventually can always recreate it if you still have access to the seed. And so this kind of prompted me to improve it by adding hardware security and the TPMs, because TPMs already provide all the primitives for some reason. To answer your question, it's not used in an operating system, but it's kind of natively used in the TPM. So the reason it actually exists, when you do TPM initialization, you create a so-called storage root key. Like if you read any TPM setup guide, and storage root key is basically generates an asymmetric key from that seed in this reliable manner. So like you can wipe the TPM, regenerate, and it will always be there. So this is like this approach is a cornerstone of how TPM works. Any more questions? Going once, twice. Thank you.